Okay, so section 4.2 is on qualitative analysis. We're going to learn how to identify unknown ions. This is going to be broken down into a two-part lecture. So today I'm just going to talk about solubility rules and net ionic equations. We're actually going to go ahead and skip the warm-up, and we're going to start down here where it says precipitate formation. Okay, so salts have different abilities to dissolve in water. And when a salt is added to water, it'll dissolve if the attraction of the cation and the anion is overcome by the solvent. So for instance, water is a polar molecule. It has a partial positive end and a partial negative end. And the partial negative end of water is going to be attracted to a cation in a salt, and the partial positive end of water will be attracted to an anion. And when a small amount of solute dissolves in a solution or in a solvent, we would say that that solute has really low solubility, okay? Whereas if it dissolves significantly, then we would say it's soluble. So silver chloride is an example of something that we talked about in the last section and this section about a substance that has low solubility in water. Okay, so how do I predict whether or not something is going to be soluble in water? Well, we have a table on the following page, and this lists some common ions and their solubility in water. And remembering this table can be a rather daunting task. We have a lot of ions, right? So we've got all the alkali ions, hydrogen ion, ammonium ion, the nitrates, which are all soluble when they're in a compound. And then we have some of the halogens, chloride, bromide, and iodide, which not all of the compounds containing them are soluble. The ones that have silver, lead, and copper tend to have low solubility. So how do we keep track of what is soluble and what isn't? Well, what I recommend you do is I recommend you take a look at see if I can move this over. This video, I'm going to play it for you right now, and it's got a great acronym to help you remember what is soluble and what isn't.
I don't see you like that. But anyways, this mnemonic does come in handy, and this image does come in handy when you need to learn solubility in chemistry. So the way to remember all the molecules or substances that are always soluble, you think of NAGSAG, always soluble elements. NAGSAG, are molecules. So the way to remember NAGSAG is to remember that whenever you sag your pants, somebody's going to nag you. So the N in NAGSAG stands for nitrates, NO3 minus. The A for acetates, C2H3O2 minus. And G for group 1, the group 1 metals such as lithium and sodium and many more. S is for sulfates, which is SO4 minus 2. A is for ammonium, NH4 plus. And lastly, of all the soluble ones, group 17 nonmetals, such as fluorine, chlorine, bromine, iodine, and more. Even though I told you that these elements and molecules are always soluble, I lied, because there are two specific groups that are exceptions. Now the very first group I like to call PMS, and it's very easy to remember, it's just 3 letters. And the P stands for Pb plus 2, which is lead. The M stands for mercury, diatomic mercury, Hg2 plus 2. The S for silver, Ag plus. And the second exception, or before I go into the second exception, I'm just going to make things easier for you and put a nice magenta asterisk next to PMS, and then put a magenta asterisk next to the sulfates and group 17 nonmetals, because PMS is never soluble with the sulfates or the group 17 nonmetals. Now let's move on to the second and final exception. This exception is called Castrovere. Castrovere. And Castrovere, the reason it's given that name is because it's calcium, strontium, and barium, all from the alkaline earth metal group. And Castrovere is never soluble with sulfates. So you see that beautiful neon green asterisk next to Castrovere. Well, we're also going to put one next to the sulfates because it's never soluble with the sulfates. And I suppose since now we know 2 exceptions to NAGSAG, NAGSAG is not always soluble, but it's almost always soluble. Good luck with your solubility.
Okay, so This is a great, great trick. All right. So I recommend, this is posted on Canvas, so you can watch it as many times as you want. Okay. But I really recommend you use it to help you remember what's soluble and what isn't. Because if you look at this, I mean, this is a long table, right? That's pretty comprehensive. So just use NAGSAG. So what we're going to do is we're going to practice using the solubility rules to predict whether a salt is soluble or has low solubility in water. Now, depending upon what textbook, teacher, class, online resource you're looking at, sometimes they will replace low solubility with insoluble. Okay, you're going to see that most of the time. So I just want you to be aware of it. So let's take a look at 1A. We're going to classify the following as being soluble or having low solubility in water. Calcium sulfate, which is CaSO4, we need to look back at the solubility table over here, and sulfates are down here, okay? Do you see how we have the calcium ion here? So the calcium ion with sulfate has low solubility, okay? So 1A is low solubility. B, iron 2 sulfide, which is FeS. If we look back at the table, sulfides are down here. Well, it's soluble with all of these substances. I don't see iron listed, do you? So that means it would be under the all others and it would have low solubility. Are you following me so far? Okay, so 1B is also low solubility. C, strontium hydroxide, SrOH2. So if you look back here, towards the bottom, hydroxides, if it's with the alkali ions, hydrogen, the ammonium ion, or strontium, then it would be soluble. Okay, so we're going to put here that 1C is soluble. Can you take D through F? And let's see what you guys come up with. Okay, what did you get for D? Soluble? How about E? Isn't it soluble? Yeah, isn't cesium in group 1A? Yeah, so I believe this would be soluble. And then the last one. Soluble. Okay? Okay, let's skip number 2 and let's go to number 3. A student is given a sample of a solution that is either magnesium nitrate or strontium nitrate. Okay, so magnesium nitrate is MgNO3 2, and then strontium is SrNO3 2. And this is a solution, so that means it's dissolved in water, so I would put AQ after it. When a few drops of a solution of sodium hydroxide is added, no precipitate forms. So that means they took each one of these solutions and they added sodium hydroxide, which is a strong base, and they didn't get a precipitate. Does the sample contain magnesium nitrate or strontium nitrate? Well, what we could do is write out a double replacement reaction and then use the solubility rules to write in the states of matter. Okay? So remember, when we're doing a double replacement reaction, you're going to take the cation in each compound and you're going to switch them. So magnesium will come over here, sodium will come over here. So that means you'll have sodium nitrate and magnesium hydroxide. And in the second one, strontium will come here, sodium will go here. We'll have sodium nitrate again, followed by strontium hydroxide. Now I want you to look at the solubility rules and tell me what the states of matter will be on the products. Remember, if it's soluble, it will have an AQ. If it has low solubility, it will be a solid. So what do you think? What are nitrates? All nitrates are soluble. So these two would have an AQ after them, okay? And then look at your hydroxides. Magnesium hydroxide has low solubility, so this would be a solid. This is soluble, right? Okay, so if we formed a solid here, this is a precipitate. Okay, so that means we must have strontium nitrate because no precipitate formed when they added sodium hydroxide. Questions on that? Okay, so I'm going to spend the rest of class focusing on how to represent a precipitation reaction in solution. There are 3 different ways to represent it. The first is with a formula equation. This is simply a balanced equation with the states of matter. Okay. Sometimes they call the formula equation the molecular equation. Okay. So this here is an example of a formula or molecular equation. It's balanced. I have the states of matter for everything, okay? Okay. The second way of representing a precipitation reaction is with a complete ionic equation, okay? A complete ionic equation is when you break down anything with an AQ into ion form. Now, make sure you make a note that this does not include weak acids or weak bases. And the reason why you're not going to break down a weak acid or a weak base is because they only produce ions less than 1% of the time. So we wouldn't have a significant amount of ions present, okay? And you're going to leave solids, liquids, and gases alone. Like, you're not going to touch them. You're going to write them exactly as they are in the balanced equation. Okay, so here you can see from my formula equation, do you see how we have an AQ here, here, and here? Okay? None of these are acids, so we don't have to be concerned, are they a weak acid or not? They're not bases either. So I would write 2K plus 1 2I negative 1. I have a Pb plus 2. I have 2 NO3 negative 1. I have 2 K plus 1s, and I have 2 NO3 negative 1s. This solid stayed exactly the same. I didn't break it down. Okay, so that's how you write a complete ionic equation. All of these lead us to the third type, which is a net ionic equation. Okay? Net ionic equations contain the ions that participated in the reaction. And what we do is, to get from the complete ionic to the net ionic, I cancel out whatever ions are the same on the left and the right side. So here, do you see how I have 2K plus 1s on the left and the right side of the balanced equation, or of the complete ionic equation? So these would cancel because they're identical. They're actually watching the reaction take place. They're called spectator ions. So they don't participate in the reaction, so I get to cancel them. Then I have 2 NO3 negative 1s on each side. Those also cancel. So all of these that I just canceled are spectator ions. And when I cancel them, I get my net ionic equation at the bottom here. The only thing that you guys need to watch out for is, when you get to your net ionic equation, you want to make sure that the ions add up to whatever precipitate you formed. So I have a lead 2 ion, I have 2 iodide ions, I have 1 lead ion here and 2 iodide ions. So these added up to this. That's kind of your check, so you know you did it right. Okay? If you have coefficients that are all divisible by the same number, then make sure you simplify them. So make that note. If coefficients are divisible by the same number, simplify. In this case, my coefficients are 1, 2, 1. They aren't all divisible by the same number. There's nothing I can do. So I would leave it. Okay? So let's take a look at the quick check. We're just going to practice writing net ionic equations, okay? So let's look here at 2A. We're going to write the formula equation, the complete ionic, and the net ionic. So this is what you're going to have a quiz on next class. The quiz will be on paper. I will give you one problem. You'll be given the reactants. You'll have their states of matter. You'll predict the products. You'll write the formula, complete, and net ionic equations. You'll predict the solubility of the products. So meaning, is it AQ or is it solid? And you'll do that because you'll remember NAG-SAG. Does this make sense? Okay. So here, you have a solution of strontium hydroxide mixed with silver nitrate. So strontium hydroxide is this. And since it's a solution, you would put an AQ after it. Then you have silver nitrate, AgNO3, also a solution, so it will have an AQ after it. Okay? I'm leaving a space in front just in case I have to balance it when I'm done. This is a double replacement reaction, so the strontium and the silver ions will switch places. I'll get silver hydroxide and strontium nitrate. Now what I want you to do is look at your solubility rules and tell me, what will the state of matter be for my products? AQ where? Sorry. Yeah, aren't all nitrates soluble in water? So this would be AQ. How about the silver hydroxide? This is a solid because it has low solubility. Do I have everybody so far? Okay. Is it balanced? No. What do I need to do? Good job. Okay. So we just wrote the formula equation, also known as the molecular equation. Okay. Do you want to practice writing this in complete ionic form? Okay, so which ones are you going to break down before you even do it? Just the AQs, right? So this one, and this one. Go ahead and write the complete ionic equation, and let's see what you came up with. Okay, did you get what I got? Okay, now let's look for what is exactly the same on the left and the right side. I've got a strontium ion here, and then I have another one here. Do I have anything else that's identical? NO3s. I've got an NO3 here, and I've got some over here, right? So just so you know, they have to be exactly the same. If they aren't exactly the same, you may have done something wrong. So what I just boxed in, these are my spectator ions. They watch the reaction taking place. They do not participate. Therefore, I will cancel them to get my net ionic equation. But before I write the net ionic equation, let's take a look at some coefficients. The coefficients in everything remaining, they're all 2's. Aren't those all divisible by 2? So doesn't that mean my coefficients will simplify to 1? So my net ionic equation will be OH -1 plus AG plus 1, and then we have silver hydroxide. Do you see how my ions added up to my solid product? So can you do this on a quiz without me? Yeah? Do you want to practice one more on your own, just to make sure? Okay, why don't you try B, and let's see what you came up with. did you do? No problems? Any questions? Yeah.
So when the first equation, how did you know that it was the AQ? So you go in here, and since it's not like
Here
okay, so you go to
or
square
there?
one.
Reactants or products?
The reactants.
Okay, so
I got it. I see it now.
okay, so yeah, if they tell you their solutions, automatically AQ
Okay.
for the reactants. Okay? So you're going to have to do this on paper. It is worth a lot of points. Okay, so for instance, you would have the reactants given to you with their states of matter, but you'd have to predict the product formulas and the states of matter on the products. So it's a point each one. Okay, and then when you get to the complete ionic equation, it would be a point for every single ion that you wrote. Okay, same thing on the net ionic equation. So like I broke it up into pieces just like this. Like this is exactly what it's like. Okay? So any other questions for me? Do you want to do the last one? Just to make sure you got enough practice? Okay, take a look at C. Okay, so any questions for me?